Projections. So previously in the materials we saw these frames of references and how the projection matrix plays an important part there. We saw different projections. One of those was this orthographic projection. So this orthographic projection takes this big box and squishes it down into this -1 cube and then projects it to a screen. It does not have this perspective distortion. So objects further away do not get smaller. So no matter how far away your object is, it's still flatly projected onto the screen. Now this orthographic projection is defined by its view volume, by its left, right, top, bottom, near and far planes. So those planes, these numerical values, just define this big box. That's the view volume that gets projected down, and everything inside it we should see on the screen. For example, in 3GS, you define it exactly like this. Left frustum plane, right frustum plane, the top plane, bottom plane, near plane, far plane. So this is directly from the documentation. Or with GLM, you define the orthographic projection matrix by the same parameters. Now this orthographic projection matrix consists just of range mappings. So we have defined this big box from left to right, bottom to top, and near to far. And we want to squish it down into another box from -1 to 1. So all that the matrix will consist of, all that it has to do is just map those 3 ranges into this -1 and 1 range. Now how do those range mappings work? So let's imagine we have a range from left to right. So this is some specific range. We have some values x along this range, and the axis goes from here to here. The first thing we want to find out is the midpoint of this range. So this is just right plus left divided by 2, so the middle value in the range. The next value we want to find is this d, this distance d, that's from the midpoint to the end. So this half of that length. So this is just right, the larger value, minus left, the smaller value, divided by 2, so that's half of the length of this range. Next, we subtract m from everything. So if we subtract m, the midpoint, then we move our range from left to right to minus t to d. Why? Because this m, if we have a value at m and we subtract m from it, then we get 0. So this midpoint, this goes to 0. And everything else goes along with it. But the endpoints now are just half the length to the positive axis and half the length to the negative axis. We have now transformed our range from left to right to minus t and d and centered it around 0. And now the next step is very simple. We just divide everything by d because we want to get to the range -1 to 1. So if we have minus t, we divide it by d, we get to -1. If we have d, we divide it by d, we get to 1. So we're going to squish this range down into this -1 to 1 range. And this is basically what the range mappings do. Now if we write all of these things out, we get this perhaps quite horrible equation, but if we simplify it, we get this scale factor for all our values inside this range, and we get this translation value that needs to be subtracted from this factor. And this calculation does this range mapping from left to right to -1 and 1. And thus these range mappings for all of the ranges from left to right, top to bottom, and near to far, they're encoded in the orthographic projection matrix. All these values do is the range mappings from this big box into this -1 to 1 cube. Next is perspective projection. So this is now a projection that does include this perspective distortion. So things further away get smaller, things near the camera will get bigger. Usually it's defined by the vertical angle of the field of view, some angle for the camera, then the aspect ratio of the screen, and the near and far planes. The aspect ratio of the screen is just the width of the screen divided by the height of the screen. For example, here in 3GS we have perspective camera, field of view, the camera frustum's vertical field of view, the frustum's aspect ratio, the near plane and far plane values. Also in GLM, same thing, field of view Y, aspect near and far. So next we're going to try to figure out how to convert this complicated frustum shape into this normalized device cube, this canonical view volume. To do that, we see how should we transform the coordinates inside this view volume to project them down to this near plane. So for that, we're going to have this point A and this projected point A'. It has coordinates x', y', and minus near. it's minus near because we're at the near plane, and well, this is the negative z-axis. So the coordinate would be minus near. Now to find out what should x' and y' be for this projected point, we're going to add another line here. So this line that is going along this z-axis, passing through point 0, 0 minus near and 0, 0 z, and then making this 90-degree angle with point A. And when we have done that, we can notice that we actually have two triangles here. The smaller one down here and the larger one sharing the same angle. And from high school you might remember that these are similar triangles. And with similar triangles we can try finding the lengths of these legs by knowing the lengths of other legs. For example here, the length of this leg on the smaller triangle is near, because this is exactly the distance from the camera to the near plane that we defined in the constructor. The length of the same leg on the larger triangle is minus z, because it ends at 0, 0, z, but z has negative values here because we're at the negative z-axis, so the length will be minus z. Then we have other two legs here. So this is the length x', so this is what we're trying to find, the x-coordinate of the projected point A'. And then we have just the x-coordinate of our original point A. Knowing about these similar triangles, we can just write out that our x' divided by x will be the same ratio as near divided by minus c. So x' divided by x would be the same as near divided by minus c. And then we can just do the cross multiplication here and find out that x' is near times x divided by minus c. And now we have come across quite an interesting situation. So the coordinates of the projected point A', the coordinate x', for example here, needs to be divided by another coordinate, by minus c. This is something we haven't done before. So with regular matrix vector multiplication, we just multiply different coordinates together with different scalar values, but we cannot divide by another coordinate. But here, in the perspective projection, we have to divide x with minus c. And this makes some sort of sense if you think about objects in the real world. So if they're far away, if z, distance from us, the viewer, is large, then they become smaller. So it makes sense that we divide their x and y coordinates by z, by the distance that they are away from us. If they're far away, then z is larger and they become smaller, and if they're near us, z is smaller and they become larger. Now there is one more thing missing here, so we want to map these values also to the minus 1, 1 range. So we can just normalize these values by dividing x with right and y with top. And now to encode this calculation in the matrix, we can just take out the scale factors, put them on the matrix's diagonal, and then move this division with minus z to the last row of the matrix and doing it in the homogeneous division. So this is what the matrix would look like. On the diagonal, we have those near divided by right and near divided by top factors that we found over here. And now this division by minus c, for that we're going to change the last row to be 0, 0, minus 1, 0. What it does is it sets the last value that was 1 before to minus c. So when the homogeneous division happens, then all of these coordinates, this near divided by right times x, near divided by top times y, will get divided by minus c. Just like we needed over here. Now we're still missing this third row. So what should we do with z? If we just put 0, 0, 1, 0 here, then we will get z, and well, z divided by minus z would be minus 1, and we would lose all of the z information. That would be bad because we wouldn't know which fragments would be in front of other fragments. Thus we want to actually transform the z such that the result would be mapped from the range minus near to minus far to minus 1 to 1. So all the z's that are between minus near and far will get mapped to minus 1 and 1. For that we can use some scale and some translation. If you write out the equation what is happening with z, then we see that it's the scale factor times z plus the translation factor divided by minus z. And that would be our transformed z. And now we want it to be transformed in a way where all the z's that are at minus near will get transformed into minus 1, and all the z's that are at minus far will get transformed to 1. So we have these two equations. Now these minuses are a bit bothersome, so we can simplify these a bit. The minuses down here cancel out, and we are left with one minus in the front. Now we have a system of linear equations. There are two equations. We have two unknowns, the scale factor and translation, And this system of equations can be solved for S and T because it's well defined. We can use something like Wolfram alpha to come up with a solution, and well, there is this one solution, and this looks like that. So the scale factor would be this, and the translation factor would be that. And here again we have these minuses, and we can get rid of them by moving the minus down here. So if we exchange near and far, we get rid of the minuses at both elements. Now by multiplying z with near plus far divided by near minus far, and adding 2 times near times far divided by near minus far, we get values that are mapped to the range from -1 and 1. But this mapping is not linear. Turns out that this is a hyperbolic mapping. The values, the transformed z values, are mapped to this hyperbolic curve because we're dividing by z in the same equation. So this division by z, while there is a solution to map it from -1 to 1, it results in this hyperbolic curve. And this value is called the depth value. It is from -1 at the near plane to 1 at the far plane. So in this example I've set the near plane to 1 and far plane to 10 so that the curve would fit nicely on the screen here. And you can see that the values from -1 to 1, they change quite rapidly near the near plane. So near the camera we have lots of changes, but further away we get from the camera, the changes become less and less. So they are all closing in on this value 1 at the far plane, but they're very close to each other. They don't change order or anything, just that the granularity gets less the further away you go in this view volume from near to far. This has some implications which we'll talk about later on in the materials. We can also define this perspective projection matrix with the field of view, the angle alpha, and the aspect ratio r. So those two terms on the diagonal, they're exactly the same values that were there before, except that now they're defined by the field of view and the aspect ratio. So from this video you should understand two projections: orthographic projection, its view volume, this big box, and how that is transformed into a canonical view volume by these range mappings that are applied in the orthographic projection matrix, so P-ortho. The second projection was perspective projection. You should understand its view volume, this frustum shape, and how that is transformed into the canonical view volume. So first the projection of the x and y coordinates, so what are the projected x and y coordinates of our geometry, and then the mapping of the z coordinate into depth, and how all of these things are encoded in the perspective projection matrix P.